Welcome everybody to Calculus BC. In today's episode, we're going to be discussing chapter 9.10, which is the Taylor and Maclaurin series, which actually is a bit of a backtrack considering where we've been. In the last couple chapters, we've been learning about the power series. In fact, I have a lot of the power series that you guys should hopefully recognize right here. Okay, and so hopefully these are all power series that we recognize, right? We know that 1 over x is resembled by this series, e to the x is resembled by this series, and so on and so forth. But up until now, it has been, new driver. Up until now, it has been almost taken on faith, right? That the power series are representative of their respective non-polynomial counterparts. And we saw this by plugging things into a calculator and making the top summation term go to infinity or large numbers. And what we saw was that this sign, or that this power series here became more and more sign-looking, right? This this deal here, this power series here began to resemble more and more like cosine. This guy definitely resembled e to the x. We even took his derivative and saw that the derivative of this polynomial ends up becoming himself. And so, we have a pretty good intuition that these polynomials do in fact represent their non-polynomial counterparts, but it's not enough just to have the intuition. Today's lesson is learning the origin story of these power series. That way we can know beyond a reasonable doubt that what we are doing is the right mathematical thing. So, how do we begin extrapolating a particular Taylor or Maclaurin series? Well, I'm going to take this top guy up here, this 1 over 1 minus x. And what I'm going to do is I'm going to write him down right here. I'm going to say f of x is equal to 1 over 1 minus x. And then, in a different color here, I'm actually going to write a polynomial counterpart to him. Now, this polynomial, p of x, is going to be, I'm going to write down just the most generic polynomial I can think of, and that's going to be a plus bx plus cx squared plus dx cubed plus ex to the fourth plus fx to the fifth plus dot, dot, dot. And it could just keep on going forever and ever and ever. So what I'm going to do is I'm going to make the association. I'm going to make a comparison. I'm going to compare and associate f of x to p of x at every turn. I'm going to compare f of x to p of x. I'm going to compare f prime of x to p prime of x, f double prime to p double prime, and so on and so forth. So let's go ahead and I'm going to go ahead and rewrite him to make him 1 minus x to the negative 1 power. That's going to make my taking of the derivatives a little bit simpler. So when I take the derivative, I'm going to get f prime of x, and that's going to be negative 1 minus x to the negative 2 power times negative 1 for chain rule. I'm going to actually simplify him out a little bit. That's an arrow right there. That's going to become 1 minus x to the negative 2 power, or he can be seen as 1 over 1 minus x squared. Either way, right? It's just a bunch of equal signs here. We're doing okay. So f double prime of x is going to be, I'm going to take the derivative of him because he's easier to work with. So that's going to be negative 2 parentheses 1 minus x to the negative 3 times negative 1 for chain rule. That's going to get me 2 times 1 minus x to the negative 3, which will become, 2 over 1 minus x cubed. So I'm going to go and do it again. F triple prime of x is going to be, I'm going to bring down that negative 3, but I'm not going to multiply them in. I'm going to call them negative 3 times 2, 1 minus x, and you'll see why I'm doing this in just a second, but not quite yet. This is going to become 3 times 2 times 1 minus x to the negative 4. Eventually, it's going to become 3 times 2 over 1 minus x to the fourth. If I take my fourth derivative, that's going to be, looks like I'm going to take the derivative from here, negative 4 times 3 times 2, 1 minus x to the negative 5 times negative 1 for chain rule. And that's going to turn into, it's actually going to become 4 times 3 times 2 times 1, which is going to be 4 factorial. In fact, I could call this guy 3 factorial times 1 minus x to the negative 5. which then becomes 4 factorial over 1 minus x to the 5th power. Okay, so let's see what my polynomial counterparts are going to look like. So again, all I've done is I've taken 4 derivatives. A lot of calculus work right here, but we can handle it. So from here, p prime of x, right? Remember, a through f are all constants. So that's going to be b plus 2cx plus 3dx squared plus 4ex cubed plus 5fx to the 4th plus dot, dot, dot. P double prime of x is going to be 2c plus 3 times 2 dx plus 4 times 3ex squared plus 5 times 4 fx cubed. P triple prime of x is going to be, the 2c is going to go away. That's going to be 3 times 2d. I'll go and call him 3 factorial d plus, I'll call him 4 factorial ex, ex plus 5 times 4 times 3 fx squared. So now I'll go ahead and do my 4th derivative. So my 4th derivative is going to be, my 3 factorial d is going to go away. I'm left with, whoops, I think I missed an x right there. That's going to be 4 factorial e plus 5 factorial fx. Okay, so now I've taken a lot of derivatives. We're going to start making some associations in just a second. Okay, so what I'm going to do next is I'm going to go ahead and make the associations now. So remember, f of x I'm going to associate with p of x, f prime to p prime, f double prime to p double prime, and so on and so forth. Now I'm going to go ahead and do this at x equals 0. I'm going to go ahead and associate at x equals 0. So that means that I'm going to go ahead and I'm going to go and find out what f of 0 is. I'm going to find out what f prime of 0 is, f double prime of 0, f triple prime of 0, f quadruple at 0. Now again, how am I going to do this? I'm going to go and plug 0 into here, 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 and here, and up here too. Right? So I'm going to plug it into all of them. So if you want, hit the pause button and try and beat me to it, and then that way we can go ahead and find out what we're supposed to be. So from here, if I go ahead and let f equal 0, I get 1 here, I get 1 here, right? And then f double prime of 0 is actually going to be 2. F triple prime of 0 is going to be 3 times 2, or 3 factorial. F quadruple is going to be 4 times 3 times 2, or 4 factorial. All right, so hopefully that makes enough sense to you guys. Then I'm going to find out what p of 0 is. P prime of 0, p double prime of 0, p triple prime of 0, and p quadruple at 0. Okay, so what is p of 0? Well, p of 0, I'm going to go and plug that into here. That's a. So that's a. P double prime of 0, that's going to be, or rather p prime of 0, p prime of 0 is going to be what happens if I plug 0 into here, 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 and here. That's going to leave me with just b. And again, feel free to hit the pause button here if you want to. P double prime is going to get me 2c. P triple prime of 0 is going to get me 3 factorial d. And then p quadruple prime at 0 is going to be 4 factorial e. Okay, so at this point in time, remember, I am going to try to make these associations. So if f of 0 equals 1 and p of 0 equals a, hopefully it's not too much of a leap to say then that a equals 1, because I'm associating f of 0 to p of 0. Hopefully it's not too much of a stretch to say that b is equal to 1. That 2c is equal to 2, making c equal 1. 3 factorial d equaling 3 factorial, making d 1. And e, you guessed it, is 1. So we found out the the values of all of these letters. What I'm going to do now is I'm going to take all of these values and I'm going to plug them back into the original polynomial. I'm going to plug them back into this guy, and let's see what we get. So over here, I'm going to replace all my a, b, c, and d with 1. So p of x is equal to not a, but 1. Not b, but 1x. Not cx squared, but 1x squared and x cubed and x to the 4th plus ... And I'm hoping that at this point in time, this is looking familiar, as we have already encountered this series before. And if you remember correctly, when we were first introduced to that series, we established that this was a geoseries because r was equal to x, so we were able to find his sum. S was equal to a sub 1, which is 1, over 1 minus r, which is x in this case. And I hope that function looks familiar because we have definitely seen this guy before. So, the Taylor series and the Maclaurin series really is the origin story of the power series. What we've been doing this whole time, every time I gave you a power series, what's been happening is I've been taking 53 derivatives of my polynomial and a bunch of derivatives of my actual function and making the associations for you without you guys realizing it. So that is the introduction to the Taylor series. When we come back in a second, I will go ahead and define it for you, and then we'll do some Taylor series exercises. Give me a second. So a Taylor series really is just using an infinite series to approximate a non-polynomial function. And the Maclaurin series is just a Taylor series centered specifically at x equals 0. So whenever you see on the AP exam, if they talk about a Maclaurin series, you can assume the center is 0. Sometimes they say the Taylor series centered at 0. Just different ways of expressing the same kind of idea, but we're going to encounter both in this video. We're going to encounter centered at 0, we're going to encounter centered not at 0, and all that mumbo jumbo. So why don't we go ahead and move forward into extrapolating a more efficient formula to find out what a Taylor or Maclaurin series is going to be. So as we saw that our quintessential generic polynomial looked like this: a plus bx plus cx squared plus dx cubed plus ex to the 4th plus fx to the 5th plus gx to the 6th plus ... Right? And so now from here, I'm actually going to go and pause it, and I'm going to take several derivatives of him, and then I'll come back. If you want, pause and go ahead and beat me to the next derivatives. That way we can start making some associations. I'll be right back. Okay, so I've taken 4 derivatives now, and now what I'm going to do is I'm going to go ahead and make my associations at 0 once again, but I'm going to do them very generically this time, okay? So I'm going to go and say, all right, remember, we made f of 0 equal p of 0, and we knew that p of 0 was equal to a. We knew that we made f prime of 0 equal p prime of 0, and we knew that if I plug 0 in for all of these guys, I get b. F double prime of 0 equals p double prime of 0, and that equals 2c. F triple prime of 0 equals p triple prime of 0, and that's going to equal 3 factorial d, and f fourth derivative at 0 equals p fourth derivative at 0, and that equals 4 factorial e, and so on and so forth. So here's what I'm going to do now. I'm going to go and solve for each of these letters in a very generic sense. I'm going to say then that f of 0 equals a. I'm going to just remove the middleman here. I'm just going to remove the middleman. And I'm going to go and say that f prime of 0 equals b. I know that 2c equals f double prime at 0. So that means that c equals f double prime of 0 over 2. And I'm actually going to go and call them 2 factorial, even though I know they're the same thing. I just like having a rhythm. That's how I like to do calculus. D hopefully it's not too much of a stretch to know that D is going to be F triple prime of 0 over 3 factorial, and E is going to be F quadruple of 0 over 4 factorial. Okay, so what does this allow me to do? Well, it allows me now to go back to my original polynomial and take this A and this B and this C and this D and this E and this F and this G and literally replace them with things that are faster. So I can now say then that P of X is equal to not A, but F of 0 plus F prime of 0 X plus F double prime of 0 X squared over 2 factorial plus F triple prime of 0 X cubed over 3 factorial plus F4 of 0 X to the 4th over 4 factorial plus dot, 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 and I could just keep on going for forever. So that is a shortcut on how to maneuver a Maclaurin series quickly. Now, a Taylor series, remember, a Taylor series is a Maclaurin series that is centered not at 0. So let's go and see what that would look like. A T of X would be, let's say, centered at X equals A. Well, this, let me just go and erase him, get some more space here. This would be T of X equaling F of A plus F prime of A, and I'm going to center my X. See how X is centered at 0 up here in P of X? I'm going to center him at A by saying X minus A plus F prime of A times X minus A squared over 2 factorial, F double prime of A times X minus A cubed over 3 factorial plus dot, 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 and it keeps on going. So that is how you expand a Taylor and Maclaurin series quickly. Now, here's the thing, is that notice what's happening here. It's a lot like linear approximation, right? Linear approximation used a tangent line to approximate a curve's value at a particular time. But this is going to be a lot more powerful because now, not only do you have the function's value, you have its derivative. You have its derivative, you have its second derivative, you have its third derivative, and I think I'm off on my tick marks here. That's F double prime and that's F triple prime. You have as many derivatives as you need to best mold the shape into the graph. And notice that happened during the power series chapter, right? The more terms we had, the more likely our series resembled the function in question. So hopefully that makes a decent amount of sense. I will be right back with some examples. And we are back. So from here, we're going to write, say, let's write the first 4 terms. Okay, let's write the first four non-zero terms of this guy. Okay, first 4 non-zero terms. Okay. So it's a Taylor series. How do I know? Because I'm centered at x equals ln 2. I'm not centered at 0, so it's not Maclaurin. So I'm going to go and say T sub 4 of x, 4 being the first 4 non-zero terms, that's going to expand out into f of ln 2 plus f prime ln 2 times x minus ln 2 plus f double prime ln 2 times x minus ln 2 squared over 2 factorial, plus f triple of ln 2 times x minus ln 2, running out of space here, but cubed over just barely 3 factorial. Okay, so this is my initial expansion. One might call this the shell of my Taylor series. All I have to do now is replace this guy, this guy, this guy, and this guy. How do I do that? Well, I go and start taking derivatives of my function here. So f prime of x is going to be negative e to the negative x for chain rule. F double prime is going to be e to the negative x for chain rule. F triple prime is going to be negative e to the negative x again, one more time for chain rule. So I've got 1, 2, 3, 4, 1, 2, 3, 4, I'm matched up. So now let's go and find out what the derivatives are at those exact moments in time. So that's going to be f of ln2. Well, what is that? That's e to the negative ln2. Now, before you cancel out and call it negative 2, remember the exponent's going to jump in, making him e to the ln of 1/2. Those guys finally cancel, giving you 1/2. F prime of ln2, hopefully it makes sense that you'll get the same thing but negative 1/2. And what you'll get is an alternation between 1/2 and negative 1/2. I'll go and scroll down real quick here. F triple prime of ln2 is equal to negative 1/2. So hopefully that makes sense. And then what we're going to get here is we're going to get t sub 4 of x being, the first one is going to be 1/2. So 1/2 minus 1/2 times x minus ln2 plus 1/2 times x minus ln2 squared over 2 factorial minus, right, the triple prime minus 1/2 x minus ln2 cubed over 3 factorial. And that would be the first 4 terms of a Taylor series for e to the negative x centered at x equals ln of 2. Okay, let's go ahead and go to another example. Okay, and here we are, right? The first 4 non-zero terms of y equals cos x at x equals pi. So, again, Taylor series, we're not centered at 0. We gotta do our Taylor series interpretation. So, t sub 4 of x is gonna equal f of pi plus f prime of pi times x minus pi plus f double prime of pi x minus pi squared over 2 factorial plus f triple prime of pi x minus pi cubed over 3 factorial. And 1, 2, 3, 4, first 4 non-zero terms, but if you know where this problem is going, you might see a bit of a snag. But that's okay, we will handle it. So from here, let's find out what each of these values are. What is f of pi, f prime, f double prime, f triple prime, all that mumbo jumbo. So remember, y equals cos x, right? So y prime, negative sine x. Y double prime, negative cos x. Y triple, sine x. Y quadruple, cos x. And we just keep on going down the chain. So what happens at pi? So at pi, I get cos of pi, which is negative 1, 0, right? This is going to become positive 1, 0, and negative 1 again. Okay, how does this help me? Well, when it comes down to writing the Taylor series, what I have is f of pi is negative 1. So I can start by saying t sub 4 of x is equal to negative 1. Now, when it comes to the next term, right, y prime is going to be 0. So he's actually dead. This guy's gone. But then my next term, my double prime, will get me 1. So plus 1 times x minus pi squared over 2 factorial. My y triple prime is sine of pi, which is 0, so this guy's dead, which means I have to go now to my next term, which is going to be negative, right? Because good thing we took 4 derivatives. And it'll be 1 times x minus pi to the 4th over 4 factorial. And now I've got 1, 2, 3 terms. I need my 4th term. At this point, the pattern may be recognizable, and you would get x minus pi to the 6 over 6 factorial. And those would be your first 4 non-zero terms of cosine written as a Taylor series centered at pi. Okay, I think I will wrap it up here. I actually don't have another example. I thought I did, but that will wrap it up for Taylor and Maclaurin series. So as we move forward, we will eventually learn how to estimate values of functions in those Taylor and Maclaurin series, and we will want to do it within a reasonable amount of error, a reasonable amount of wrongness, which means there's going to be the introduction to another type of error bound for the Taylor series, so look forward to it. As always, please leave comments or questions in the comments area. I will see you all in the next episode.